So hello guys, my name is Wiktor. I'm a co-founder at Goroutines, also a student at Vrije University Amsterdam, and today we're going to talk about peer-to-peer networking in Go. So first of all, a quick question. Who has done networking at all? Raise your hand. Keep your hand raised if you know about the server and client model. Keep your hand raised if you know about the peer-to-peer networking model. Great. Keep your hand raised if you know about Leap peer-to-peer. Yeah, and keep your hand raised if you know about Leap peer-to-peer, GoLab peer-to-peer. Yeah, not a lot. That's why I'm here. That's why I want to introduce the peer-to-peer model versus the server and client. We're going to talk about how the network address translation works. We're going to talk about challenges of peer-to-peer networking. And then I'm going to introduce GoLab peer-to-peer. We're going to see the whole patching procedure, the title of the talk. Everything's great?
Can you remove the badge?
I can remove the badge.
Yeah. Okay, perfect. And here we go.
OK, we're going to talk about the whole patching procedure, followed by a demo. And yeah, that's it. So let's start by talking about the differences between server and client and the peer-to-peer networking model. So the server and client model, we have two types of nodes in our system. We have the server and the client. And the main difference, the main point that I want to make about server and client is the level of authority. In the server and client model, the server has much more authority over the system compared to the client. Let's say that there is a central part, you can just turn off the server, then the clients are no longer able to communicate. This is in contrast with the peer-to-peer networking model. In a peer-to-peer networking model, everyone has almost the same level of authority, so that there's no central party who can disconnect, who can disable your application. And with this, why should you even care about peer-to-peer networking? Why should you care about the things I'm talking to you? So the main points that you can make about peer-to-peer networking, the book points, are its performance. Intrinsically, you don't have the hop between the server and the client, so you can connect directly, so there is lower latency. If you would think of a streaming application, you don't have a central server which bandwidth is divided. You can say it's more reliable, given a big enough network. If you take one node out, the network should be still operational. And I would say there are no deployment costs. I mean, the network is there. You can deploy your application. If people start using it, the network will facilitate that. So you don't need to care about infrastructure, I guess. And those are great reasons to go to your manager and tell, yeah, I want peer-to-peer networking in the next application. Those are great reasons. But you know, I'm a kid. I'm 19. I don't need to talk to my manager why peer-to-peer networking is cool. For me, it's just cool. I just like the notion of being able to talk with someone in the greater scheme, in the network, by just knowing their ID. I don't need to know their physical IP address. I just need to know their ID within the network. And that's how we can connect. That's how we can talk to each other. So with this thought in mind, let's explore what challenges we have to solve to make it a reality. But before that, a bit of NAT. We have to talk about the network address translation protocol and how it impacts peer-to-peer networking. I know many of you might know about NAT, but we have to bring everyone to the same page. So let's say this is our scenario. We have an Apple, a Wiktor. Those are two nodes connected to the internet. And Wiktor is a private node. Apple is a public node. Let's introduce some addresses so we know what we are talking about. And let's assume a hypothetical scenario where Wiktor would like to connect to Apple. What happens? So let's say Wiktor runs this following Go code, a net dial on the Apple public address. Addresses are made up, so for simplicity. And we see it succeeds. So let's go back to our diagram, see what happens. So the first thing that happens is that Wiktor connects to its NAT. It says, hey NAT, I would like to connect to Apple on this address. And what that does is it provisions a public port on Wiktor's address, on Wiktor public's address, and creates a mapping. This mapping will come important later. And what it does, this mapping allows the Apple server to send back a reply. And the Apple server sends back a reply to Wiktor's public IP with the following port. and then NAT knows to route it to Wiktor's private IP address. So let's see the connection flowing. Yeah, we connect to Apple, and then Apple sends a reply. It goes to the NAT, and NAT now consults its mapping. It knows that the address 222 should be mapped to the following private address, and the connection goes through. OK, everything works. Now let's try doing it the other way around. Let's see what happens if Apple tries connecting to Wiktor. I don't know why they would do that, but let's see what happens. Let's say Apple runs the following Go code, and as we can see, the operation times out. Why is that? Let's go back to our diagram. So the first thing that happens is that Apple connects to the NAT. It tries connecting on the port 222, but nothing is mapped there. The NAT tries contacting its mapping, seeing where should it route it in the local network. There's nothing. So it just freaks out and does nothing, and that's why the operation times out. So the main takeaway from the NAT detour, I want you to understand, is that when you try connecting to a private peer, you cannot do that. The private peer has to initiate the connection. And with this knowledge in mind, let's go further to exploring the implications of what to do so that we can achieve the world in which we can connect to someone by just knowing their ID within the network. So this is the diagram I'll be using as an example for that. So let's say Wiktor and Arthur, they are both private nodes, and they would like to connect one to another. In this diagram, I'm assuming the node name is their ID. In the real implementation, it's like a public-private key, so you know who you're talking to by public-private cryptography, so it's more secure. And we're going to take the hardest scenario so that both nodes that want to connect to each other are behind NATs. So they have to they need to punch holes in their NATs. That's what the talk is about. So the first thing that we need to solve is routing, the first issue. We need a way of, the assumption is that Wiktor connects to Arthur. So Wiktor needs to know Arthur's real IP address. So he needs to know what to connect to. And this is our first issue. Second issue is relaying. We need to establish some sort of synchronization connection. And we cannot do that directly, as we saw before. So we have to have some way of relaying the messages before we establish a direct connection. And lastly, we need to establish the real peer-to-peer connection. So that's where hole patching comes in. As you can see, all those issues require the collaboration of the whole network. They need to talk to each other, need to understand same protocols, same language. So we need some standards. Standardize those protocols, the way that they talk to each other, the way they solve those problems. So this is where peer-to-peer comes in. This is a standard pulled out of IPFS. Anyone knows IPFS? Yeah, a couple of you. So IPFS is a distributed file system, and the peer-to-peer networking part historically was pulled out of IPFS. And a specification around it was created. IPFS is written in Go, by the way. And this is where peer-to-peer was born. So let's see how we create a node in the Go implementation of peer-to-peer, the original implementation of peer-to-peer. So it's as simple as calling peer-to-peer.new. Unfortunately, by default, peer-to-peer doesn't support all those issues that we talked about. I mean, it supports it, but you have to enable it. So that's what I'm going to walk us through right now to build an example in peer-to-peer. So the first thing that we need is routing. We need a way to be able to ask the network, hey, I have this ID. What's the real address? So we need routing. This is what's called routing. And in peer-to-peer, we solve this with a distributed hash table. I'm not going to get into the details of that. I don't think I even know myself the details of that. But the important bit is that you can enable that by creating the distributed hash table on line 4, and then wrapping your host on line 10. And then on the line 19, the host.new stream call is already routed. The call already looks for a peer named Arthur in the whole network. So if there would be one, we would be able to connect to it. And the nice thing about the Go implementation right now is that it already provides bootstrapping peers. So let's imagine that we have a cold starting node that doesn't know any public address of any other node in the network. we need a way to firstly connect it to the network to any node. So that's called bootstrapping. And in the distributed hash table implementation of Go, there is a list of 6 nodes provided that you can connect to. And this is what the 13 line does. We connect to the 2 of them, and we bootstrap our node. So we have it done. The next thing that we need to talk about and to solve is relaying. Let's say we know Arthur's IP address from the previous slide. If we try to connect to it, we already know it fails from the NAT detour. We know it doesn't work. So we need a way to connect to Arthur without this issue. So what we do, as you can see right now, Arthur and node 1, they are depicted in purple. What it means is that Arthur provisioned himself a spot in node 1. Node 1 acts as a relay. So now Arthur advertises himself to the network, hey, you can connect to me through node 1. So it would look like this. Arthur connects to node 1, says, do you support relaying? And the node says yes. And then Arthur would reserve himself a spot there. And then Wiktor, going along, can connect to node 1. And now we have a connection between Arthur and Wiktor. They can already talk. Peer-to-peer supports this. This protocol is called Circuit version 2. But it doesn't support the discovery of relays by default. This is the thing that you have to enable. The subsystem is called auto relays, and the line 2 enables them. And what it does basically, it takes the nodes that we are already connected to, and goes through them, asking them whether they are the relays. And you can see enable auto relay with peer source, and this signature takes a closure. And I don't know who came with this signature. We have a maintainer who literally wrote the function, which is a bit, yeah, we have to fix that still. But yeah, details are not important today. By this, we already have a way of discovering relays and talking with relays. But we don't want a mere relay connection. We want a real peer-to-peer connection. So what do we do? Here is where the title of the talk comes in, hole punching, NAT hole punching. So being able to traverse the NAT to establish a peer-to-peer connection. I would need a bit more space and some address. Oh, yeah. Remember, this is our new diagram. And remember, the node 1 is still there. We are still connected to it. But I will leave it out for clarity. So there's, yeah. And now we need some addresses to know what we are talking about. So, OK. Now focus for a second. What do is that we synchronize through node 1. We set ourselves time t0. And on time t0, both Wiktor and Arthur send a UDP, let's say we are using UDP connect package, the packet. So the packet goes, it hits both of the NATs. Then both of the NATs create the mappings, provision the ports, and then create the mappings. So then the packets, they cross in the internet, they wave hands at each other in the internet, and this is actually a race condition. Now both of the NATs, they think that they are connected to someone while the packets are still in transit. This is the magical bit. This is why we needed to synchronize. So the packets cross in the internet. Now let's focus on Wiktor's package. It hits Arthur's NAT. Arthur NAT sees that the port 222 should be mapped to Arthur's private address on the local network. It contacts the mappings, and we have a success. We are able to connect to Arthur on his local network. We are able to hole punch through Arthur's NAT. And the exact same thing is happening on the other side. The NAT sees incoming packets. It knows that it has to map it to Wiktor's private node, and the hole punching procedure works. So the only reason we are able to succeed in this situation is because we both send the first packet at the same time, and the mappings were established. This is the magical bit. For me, this is amazing that you can do that without even thinking about it. And the best part is that you need to enable it by the line 2, peer-to-peer enable hole punching. So the whole infrastructure is there. And now the host.new stream will return only if the hole punching is successful, and we have a real peer-to-peer connection between the two nodes. So now let's do a demo of that. I have a peer-to-peer node running, not yet running, but will be running, in my university in Amsterdam. And it happens so that to connect to that university, I need to do an SSH proxy hop. So this machine right here is behind the NAT. Give me a second. Okay, we have it. Okay, and now we're starting the university node. And as you can see, it's bootstrapping. Every step that we mentioned before, it's happening right now. And it happens so that this network that we are on, or everybody is on right now today in the HOTL, is also behind the NAT node, hole punchable NAT. So if you run it and we connect to, the only thing I'm giving to in the implementation of it, there is no other addresses. There is no other identification of the university node. The only thing I'm giving is the address of the node, is the ID. So we'll let it run for a second, and in some time, and now it's connecting to the bootstrapping nodes, the ones we mentioned before. Yeah, it's already connected through the relays, and now it's trying to open a stream. So we're trying to hole punch, and we see the hole punching successful, and the data is flowing. And we see hello from Florence on the university node. So yeah, it works. Yeah. So for me, it's amazing that by just knowing their ID, we've been able to establish a connection. And this is also true if they are moving. If our university node will suddenly change its IP address, then the connection will be closed, but the lib peer-to-peer will figure out again what's the real IP address and connect to it. So if you're moving, no matter what your network status is, how you're connected to the internet, you can create a peer-to-peer connection between each other. Unfortunately, it's not all great. I mean, to enable hole punching, you need a special type of NAT called a cone NAT. I will not get into the details of it, but the gist of it is that with some types of NAT, you are unable to hole punch through it. And unfortunately, most of our mobile networks use the other type of NAT, so the non-hole punchable NAT type. So that's a pity. But in other situations, you are able to establish a peer-to-peer connection. Yeah. I want to give special thanks to William Will Kennedy. He's a guy who I met in Athens on my first GopherCon, and he actually helped me to write the proposal. He's not here today, but yeah, thanks to that guy. And thanks for listening. That would be it. One thing still I want to mention is this is the QR code for the GitHub code that you've seen, running the demo. And I also provided there an example of all the things working together. I couldn't find an example myself of AutoNAT, hole punching, and distributed hash table working together. So this is like, I think, an idiomatic example of lib peer-to-peer working there. So if you want to do something with it, there is your starting point. Yeah.
Excellent. Thank you. Now, we have time for a couple questions.
Yeah,
so
I would like to
hear from the audience. So if there are questions, there we go.
Oh no, the lib peer-to-peer guy.
No, it's overestimated. Nice username, by the way.
One time?
Nice username. What, Jurk?
Jurk, yeah. It's my names in Polish. I have 3 names in Polish, so.
Nice.
Thank you.
I was kind of curious and thinking about it. How crucial is that synchronous element to the establishing of the connection? Because if the network knows how to associate IDs with the not opened ports and no open and public IP addresses, that's what is enough to be able to establish the connection, right?
It is able to establish a connection with a public node, but not with 2 private ones. As you've seen before, like in the NAT example, maintainer, it wasn't working as we didn't have the mappings ready there on the other node.
No, that makes sense. I mean, if the node is already known to the network.
It's already known to the network?
With the diagram, right, you see the mapping from the public port to the internal private. And in theory, you could build a NAT like this, and it would work. And the problem in practice is that there's this one mapping, and there's a second mapping that mapped the public port on the NAT to the remote address. And it's going to check both mappings. And it was just, it's complicated because then you have a freeway kind of mapping. And so what happened is that that mapping is used to get the public address, and then you tell the public address to the other one, and you, for the second mapping, you need to do the race condition. And it was just like, we were discussing this actually yesterday, and we were like, no, it's too complicated, and we don't need to go into detail. And maybe we should.
So bottom line, there is another layer of complexity.
Yeah. Sorry for no answers. I'm also not a maintainer of the library, so I don't know the details and the deeds. I just use it. Any more questions?
Going once?
Going twice? None.
I think